All right, we're going to be learning about acids and bases, and what makes an acid, what makes a base. Here's just a table of just some like observable properties that acids and bases have, just so you know and you're aware of that. I'm not going to spend time talking about it. You can read it. Acids and bases, a common way of testing to see if acids and bases, to see what something is by using an indicator. So there's many different chemicals out there that we'll be using that will indicate if something is an acid or base depending on what color it turns, or actually not whether it's an acid or base, but what the pH of the solution is. Some common ones that you maybe used before and we will be using in class is, boy, I'm really having problems clicking here, is the litmus paper, and the phenolphthalein we'll be using quite a bit, and well, that's pretty much it for common ones that are on there. Okay, so acids and bases are different because of what they do in water. An acid is a substance that dissolves in water to produce hydrogen ions, or H+, and so when they're written, you'll see them written as H something. And so over here we have an example of an acid. So if I put it in water, the H separates off. So that's what makes it an acid. A base is something where when you put it into water, an OH minus separates it off. And that's really what gives acids and bases their different properties, what makes an acid and a base a base. So this is one definition of acids, is the Arrhenius acid and Arrhenius bases, and that's the definition you're just given. Some common ones are given here. If you notice that we always have H's in front of all our Arrhenius acids, we always have OH's at the back of all our Arrhenius bases. So now that's a rule that works most of the time. If you see an H at the front, probably an acid. If you see an OH at the back, probably a base. Doesn't work all the time. Once you get into organic chemistry, there's lots of H's and OH's that are there for different reasons. But in inorganic chemistry, H at the front, acid, OH at the back, base. When you have Arrhenius acids and bases, when they react together, that's called a neutralization reaction, and you always produce water and a salt. Now notice I don't say you make salt, you produce a salt. So your acid comes together and your base, and the OH comes from the base, and the H comes from the acid, they make the water, and then just the other two bits, whatever they happen to be, make a salt. So sodium chloride is a salt that's made from the reaction between hydrochloric acid and sodium hydroxide. There's a different way of defining acids and bases, and that's as using the Bronsted-Lowry definition. And so Bronsted-Lowry, instead of looking at what happens when you put them in water, because let's face it, not all reactions happen in water, is now we say an acid is a proton donor, so a proton is an H+. Okay, so when I say proton, I mean H+, and a base is a proton acceptor. So again, forget that, proton H+. So when we look at a reaction between a Bronsted-Lowry acid and base, what's happening there is we've got an H that just moves from one thing to the other. So we start off, this is our acid, this is our base. When they react, the H moves over, and now this is called our conjugate base because it was the acid and now it's the base, and this is called our conjugate acid. The reaction will only happen if you are making something weaker than what you started with. So you might start with a strong acid and a base, and you end up with a conjugate acid and base that are relatively weaker. Okay, so for example, if I take ammonia, NH3, and react it with water, one of the H's will come off of the water, and so it makes NH4 plus H2O minus, or sorry, plus, messed up, sorry. I said the minus correct, but plus OH minus. So in this case, this is our base, this is our acid. The NH3 became NH4, which is now our conjugate acid. And the OH minus, which was what our water became, is now our conjugate base. Okay, and so this happens, you know, we talk about equilibrium. This isn't really a one-way thing. It can happen both ways. So where this conjugate acid base comes from is when we're going back the other way, now the H can be thought of as going to the OH minus, and so that's acid base. With CO2 and water, okay, we'll skip that one for now. Okay, we can look at that together in class. Some acids are what's considered strong acids, which means when they're put in water, they break apart completely, and all of the H's they have go and react with water. And it's not much of an equilibrium process. It's pretty much irreversible, just like a one-way street thing. Okay, some acids are weak acids where it's only partially goes. Okay, so just because you have 1 molar HF doesn't mean that you have 1 molar H or 1 molar F. Okay, so we have the same thing with bases. Strong bases are ones that completely dissociate in water to make all OH minuses, and weak bases are one that will only partially react with water. When we're dealing with acids and bases, we talk about pH. So pH is defined as a way of measuring the concentration of H plus in solution. Its definition is pH is the negative log of H plus, and actually P is just a function. P of anything is the negative log of that thing. Okay, by negative log I mean -1 times the log. I don't mean anti-log here. Okay, if you want to find H plus, then you take 10 to the negative pH power to go that. Okay, so in water pH can be anywhere from 0 to 14. Anything lower then 7 is acid, anything higher than 7 is a base, and a pH of 7 is considered neutral. Okay, in water, your concentration of H plus and OH minus, because of water itself, breaks up. Since water is both an acid and a base, we have water can react with itself to make H3O plus and OH minus, and this is an equilibrium reaction. And so because of that, the concentrations of H plus and OH minus in water always have to be 1 times 10 to the negative 14th, which means the pH of something and the pOH have to add to 14. Okay? I think we'll probably be best just to do these example problems at the beginning of class. Okay, of how to go. I mean, certainly I think it'd be good for you to take the equations you're given and try them on your own, see what you can come up with. It's always better to try them first and then, you know, come to see what you did either right or wrong. Okay, there's 4 different properties that we can look at in dealing with acids, bases, talking about how much, what's the pH or how much H plus, what's the pOH, how much OH minus, and this is just kind of a helpful diagram of all the different ways you can go back and forth between different things. And again, we'll work a few example problems in class. Again, when we talk about, we already kind of introduced this whole idea of strong acids and strong bases versus weak acids and weak bases. When something is weak, it means that its reaction to water is an equilibrium process that doesn't favor the products very much. If something is a strong acid, we really wouldn't have this double arrow. We would have like just an arrow one way for like strong, okay? Because everything you have here goes over there. But for equilibrium, only part of it does. And the equilibrium constant for acids is called Ka, and this is how you would write the expression for Ka, and it actually was something that used Ka on your last test. And then same thing with bases. If it's a weak base, it's an equilibrium process between the base and water. And if it's a strong base, it just, nope, goes pretty much completely there and really not so much backwards. Okay? And so we can write what's called a KB there. Again, I think it's probably best just to work this one out as a class, so we'll plan on spending some time working this out when you get to class tomorrow. And I left extra room to work it out. And again, here's another one that we'll work out together as a class. We might spend the entire time working problems, which is fine because we get all this other stuff out of the way. So these ice tables that we'll be doing, you can actually, because the way you do it is the same way every single time for an acid or base, you can just say, you know what, it works the same way every time. So rather than working through an ice table every time for this, you can just come up with these equations, and we'll show you how to use these. And it gives us a handy way of going from knowing the concentration of a weak acid to knowing its pH, and knowing the concentration of a weak base to knowing its pH. Okay, and again, this is just some kind of additional notes. When you know, this is really important, is when you have a conjugate acid-base pair, okay, so when you have a conjugate acid-base pair, if you know the Ka for the acid, you automatically know the Kb for the base, because they always are mathematically related to each other, okay, by what the K of water is, and K of water is 1 times 10 to the negative 14th, and basically this here is just proving this to you, okay, so it's not like you need to write that down, so don't. What am I talking about? You don't really write things down anyways, just print these out. You don't really need to know that. I'm just showing you that how you can rearrange things. Okay, so I know I kind of skimmed through, but there's like kind of a lot of like problems I just want to work together as a class. And so, but again, you've kind of seen all the note stuff, and tomorrow when you come to class, we'll spend at least half the hour looking at how do you do the process stuff so you can ask lots of questions. Okay, so I think that's all for now.